Good morning, everyone, and welcome to today's JKMRC Friday seminar. My name is Nathan Fox from the WH Bryan Mining and Geology Research Centre at the University of Queensland. Welcome everyone here today, and thanks for joining us online. Before we begin, on behalf of the SMI and the University of Queensland, based here in Brisbane, we'd like to acknowledge the traditional owners of the land on which we meet today, and we pay our respects to their descendants. It's a pleasure today to introduce today's speaker, Associate Professor Karen Connors from our very own WH Bryan Mining and Geology Research Centre here at the SMI. By way of background, Karen is a Principal Research Fellow here at the University of Queensland, but she has over 30 years' experience in the mining and petroleum sector. This includes long-term roles as Managing Principal Consultant with FROGTECH Geoscience in Canberra, and includes earlier roles in gold mining exploration in Western Australia. Karen's speciality is integrated geological interpretation of basins, basements, Crustal architecture, and using potential field geophysics, seismic and well data. So very much in keeping with this research theme, Karen's talk today is going to be looking at the basins and basin-hosted base metal deposits of the North Australian Craton. Before we begin, for those of you online, if you can type questions in the Q&A box. And that's pretty much from me. I'll hand over to you, Karen. Thank you.
Thanks very much, Nathan. And thanks for everybody coming this morning. Hang on. There we go. Okay, so I'll start with an introduction and overview to the North Australian Craton, and then we'll look at the basins themselves and some of the key features there on the stratigraphic correlations, then a brief look at some of the base metal deposits, finish up with a focus. I'll mention this as I go through, but then we'll look at a couple of key examples, looking at the basement influence on the basin evolution and the deposits, and finish up. So Nathan's already gone through my background, but I did just want to highlight, I had 14 years with FROGTECH, and Geognostics now has taken over the sea-based products. So a lot of the things I'm showing you here, I'm referencing from FROGTECH and Geognostics, but I worked on a lot of those projects myself. So when I did this initially for a basins workshop, I sat down and looked in, and I guess I knew it, but I was still surprised to realize just how much of the lead zinc in Australia is in the north and within the North Australian Craton. So we have, 80% of the lead and zinc are in Queensland and the NT, and I've just dashed in the rough boundary of the North Australian Craton. Much of it, there's a few key age groups, but much of it's in one key age group. Now, on this chart at the bottom, this was originally from the NT, so I've added a few more dots in that have come in here. And so there is some older mineralization in the Pine Creek. Most of what we're going to look at is in the Eiser super basin in the Mount Isa region over here. Pine Creek, interestingly, so there's some stratiform lead zinc closely related to some vein-controlled lead zinc, which may or may not be related. We'll have one quick look at a younger Paleozoic MBT deposit. So you can see where we are in Australia. And for those who aren't familiar with the terminology, we're broadly divided into three major cratonic blocks. So Western Australian, South Australian, and North Australian Cratons. So these are big competence cratons. North Australian Craton is by far the largest, more complex. It's got numerous internal terrains. Make sure I'm hitting the right buttons. Some of them are well defined, and you can see I've outlined a couple other blocks in pink that I'm calling smaller cratonic blocks. So those are the more competent blocks that are there and aren't really deforming afterwards. And we'll look at some of that in more detail. Some of the other smaller terrains in here, and I'll show you a detailed terrain map, they're harder to define. Looking at basement across the North Australian Craton, there's very little outcrop. But what really stands out, we have a bit of Archean and a little bit of these older rocks in Pine Creek, and even a little bit older. But dominantly, the basement, the deformed and crystalline rocks that we see are from this age package, 1880 to 1800. There is a bit of lead zinc in those, but the main lead zinc deposits are up here in the younger package that we'll spend most of our time looking at. The North Australian Craton, as I said, because we don't have a lot of basement outcrop, although that 1880 to 1800 package is widespread, it's not, there's not a lot of outcrop. So we don't know a lot about it, but from hafnium and neodymium model ages and detrital zircons, we see a general picture that the core of the North Australian Craton formed between 2600, so late Archean, to 2200. Interestingly, in Mount Isa, this eastern zone shows slightly younger neodymium model ages. So we had a proto-core to the North Australian Craton that formed during the early period, and then final assembly is through this period with a collision of the ailerons sometime before 1864, the Numal in the east, and then the Kimberley in the west. Then, so that collision with the Kimberley affected through this, oops, hit the wrong one. Was doing this the other day. Affected the Tanami down to about 1800 and after, but it's during this transition we start depositing the widespread basin sequences over the top. So there's an outline, and I'm not going to worry about the colors of those terrains, but the more cratonic blocks are shown here in red. Those are the bigger, more competent blocks. So this is a sea-based depth abasement model. So this is regionally trying to look at crystalline basement, but it's important if you use any of these data sets to look at the reports and be aware of what the definition of basement is, because it will change in age depending on the history of the underlying basement. And that's the terrain boundary outlines on top. Oops, so now I'm not advancing. Oh, there we go. So across most of the North Australian Craton, we have our basement age is dominantly that pre-1800, but I just mentioned Irandina, we have young Paleozoic deformation, and as we come to the eastern side of Mount Isa, the rocks, although they're basinal rocks, and I'll talk about them as being part of the basin, they are deformed and metamorphosed. So in this image, in this interpretation, they are still classified as part of the basement. So I remembered I better explain what the lab is, the lithospheric asthenospheric boundary, because there's been some interesting work, a paper on it recently. So we're really looking at, everybody's familiar with moho and the base of the crust. We're looking at that upper mantle layer, continental lithospheric mantle, and there's some variations in thickness has recently been noted, a correlation with especially the large and giant lead zinc deposits and other deposit types as well. So that that 170 depth, to me, I don't understand why it in itself should be key, as opposed to just the thinning from thick to thin lithosphere rather than a given depth. So this again is from that same paper by Hoggard and colleagues, and there's a couple of GA people involved in that. So this is their map of depth of the lithosphere. You can see in blue are the deeper colors where it's the lithosphere is deeper, the boundary is deeper and the lithosphere is thicker, going into the red colors where it's thinner. So their interpretation was that at that transition, if you're rifting at the transition from thick to thin lithosphere, you are sort of in the sweet spot, so that the basal heat flow is not as high. If your underlying lithosphere is too thin, your heat flow gets too high, and your reactions, your redox reactions, are not as effective in terms of metal deposition. But if you're on that edge where your lithosphere is still thick enough, you can be extending for a longer period, end up with a deeper basin without getting too hot. But interestingly, this is a difficult surface to interpret, and there are a lot of variations, and there's some new work going on. This image in the lower left is just a difference grid between this lab depth and a new model developed that integrates several different data sets to by inversion to estimate the depth of the lithospheric, asthenospheric boundary. So there's new work coming out and different methods. It's a very interesting thing to think about because, as they've highlighted, it gives you a zone to really think about. If that 170-kilometer depth is really significant, it sort of narrows your focus when you're thinking about exploration. But I think we need to integrate the basement and crust in a little more detail, and that's part of what I'll talk about today. So the other feature that we notice, and I haven't put in an image on this, is that the edge of the Cretaceous lines up with this boundary as well. So there are some young effects that we can see there with probably with the uplift and rebound. And the steeper, in parts, we have a steeper gradient or a more moderate gradient on that boundary. And I think that's part of what we need to look at and just look at those variations. Now, MOHO, basic crust, there's several data sets and there's various types of data that are used to generate this. But you can see we've got a broadly similar shape, and I've added that 170 contour and that thick dashed line. So you can see the correlation there. We can see where we're going from thick crust to thin crust. One area that I will talk about where I've got a no data there in Arnhem, this is an area that I have more questions about the lab depth. Other areas seems to make more sense. And that once you have the sea base top of basement and you have the MOHO, you can calculate the crustal thickness. So again, that looks fairly similar, but it gives you some slightly different information. Dominantly, we have deeper MOHO, thicker crust through this central area where we've had more young deformation and orogenic events. So looking at the basins, so this is the same chart that I showed you earlier, focused on the NT. I've added Mount Isa, Queensland in there beside it. Again, the lead zinc deposits highlighted by the purple stars. So this chart at the right is from Griffin et al., and it's a really interesting study on detrital zircons from present day drainages. So they were just looking at the ages that showed up. One of the key things they noted is there's this trend here, and they're highlighting in blue where we have juvenile input, and that just means we have new material coming from the mantle as opposed to continually recycling material from the crust. So we see that increasing, and that's related to Soldiers Cap Corydala groups. So that relates to what's happening in the crust and to the evolution of this area, and we'll come back to that juvenile input. So the next map I show you will be focused on this age period, the Eiser super basin broadly, and its extent, because across the North Australian Craton, it's huge. When you look at that purple outline, it covers most of the North Australian Craton. It's about 1,500 kilometres wide, over 1,000 kilometres north-south, and that's just what's left today. So this is a vast basin, but we do see in there's some localized fault-controlled depot centers. Now, remember the sea-base map we're looking at includes all those post-1800 basins. So the depot centers, and we'll look at these on another map where I've got the purple arrows. We have north-south trending depot center. Here, Lawn Hill, we have a more east-west trending depot center, and a significant one here in the Soldiers Cap group, Eastern Fold Belt, that doesn't show up in this data set, as I explained earlier, because of the definition of basement. Sequence stratigraphy, I don't want to get into in detail, but it's about the correlations, and it's about thinking about changes in sea level, where are the main unconformities, what's our accommodation space, what's happening to the crust that's either creating accommodation space or reducing it. And so that it gives us a bit more basis for correlating some of these key units from east to west. So we have a long period where we have continental, whoops, sorry, keep hitting that with the edge of my thumb, where we have shallow water deposition, we have a rapid change to deep water deposition, and that's summarized in this chart at the top. So we have the Sin Rift, we have a major extensional event at around 1680, 1675. Sabella batholith is placed in the west. Soldier's Cap Group is deposited in the east, the Sin Rift, and then with thermal relaxation, the crust subsides and sea level rises. So with that sea level rise, we have the transgression across and heading to the west and depositing these units to the west. So the stars there show Cannington, which is a broken hill type deposit, Dougal River, which a lot of people suggest might be in between that broken hill type or Cannington type, and Mount Isa, George Fisher. So you can see the relative positions that they sit relative to this margin, going from more continental in the west to more basinal or oceanic in the east. So we also see a distinct difference from oxidized brines at Mount Isa reacting with reduced sediments to trigger metal deposition at Mount Isa. In contrast, in the east, broken hill type at Cannington, we have reduced fluids interacting with oxidized seawater to cause metal deposition. And we see, when we look at the lead isotopes, we see a distinct difference. Again, in the east, we have this juvenile signature to the lead isotope saying, okay, we've got that mantle input, and that relates to crustal thinning. And whereas at Mount Isa, we have a more evolved source, which means we're just recycling older crust. And that just shows that difference in map view from Cannington here, Dougal River sitting in the middle, over to Mount Isa and up to MacArthur River. And we'll take a quick look at those deposits. But first, just looking at the basins. So we're just looking at the Isa Super Basin package here, and you can see the difference in those stratigraphic charts going across from Mount Isa up to MacArthur, and we'll look at a map on the next slide. And I think the difference we're seeing here is where we have a more complete sequence, and these sequences are thicker. That's where we have our main depot centers. Here, the Fickling group is essentially just the margin to this main depot center to the south. Mount Isa, which hosts the large Mount Isa and Hilton George Fisher ore bodies, is probably quite a small localized depot center. In map view, and this is just the Northern Territory because it was one I had available, starting from the southeast, the Lawn Hill platform, which is actually just off this map into Queensland. We have 8 to 10 kilometers, and I'll show you a seismic section of that Eiser group coming into the north-south trending Batten and Walker fault zones. We have 3 to 4 kilometers. But when you step outside of those depot centers, you can see the geology that's just shown in the pink units. That's the uppermost stratigraphy. That's all we see. So again, we had that rift, we had deposition localized in that rift, and then as we had thermal relaxation, sea level, we had relative rise in sea level, and that's when we deposited stratigraphy on those shelfal units. And that's something that hadn't really been brought together in this area previously. So we have a large area of younger cover here in Beetaloo, and that's where everybody's looking for shale oil, shale gas in the younger package that sits over top, the Roper group. We come to the west in the Birrindudu Basin. We're almost at the WA border. And we have 1 to 1.5 kilometers of sequence and outcrop, and the seismic, we've got a fair bit of seismic here beneath the Beetaloo. We see a fairly consistent 1 to 1.5 kilometers within that seismic data. So you'll just note we've got the north-south trending depot center and the east-west trending depot center. And I'll take you through, sorry, running behind, the links through to basement. So briefly looking at the deposits, and just to highlight a few key things, because there's been so much debate about these deposits for so long, and especially Mount Isa itself, where we have the large copper ore bodies, as well as the lead zinc. And you can see this chart I've taken from a recent paper by Cave and colleagues at Adelaide. You know, there's been the models, is lead zinc early and copper late? Are they both early and then remobilized, or are they both late? And it's recent studies from George Fisher, HYC, Tina, and Mount Isa are all showing not SEDEX. So the traditional SEDEX definition thought about expulsion of metal-bearing fluids at the seafloor. So that's, you know, study after study is showing that's highly unlikely. We're dominantly looking at carbonate replacement during diagenesis, and that's consistent with some of the lead age dates that we've had for a while on these deposits. We certainly see halite units in some areas, but the ore bodies themselves, the lead zinc ore bodies, are dominantly replacement, but early replacement. And part of the complication relates to the fact that there are multiple stages of alteration and mineralization, and definitely remobilization. So at Mount Isa, recent work clearly shows the copper is definitely late, and Cave and colleagues suggested the lead zinc is as well, but I suspect there'll be more work there. So we've got a series of extensional events when we look through this Eiser group chart, and a significant one here during emplacement of the Sabella. Significant pulses we see in the seismic. We see big growth packages in some of these units, but we also have minor inversion events at river time, another one here after term before lawn, and then the big Mount Isa shortening coming in later. And it's interesting because convective fluid flow by the CSIRO group is shown at HYC. You can generate fluid flow during extension, but it's much more effective during compression. So we'll just quickly step through a few of the ore bodies so you have a look at a few key features. We'll start in the northwest at Tina, HYC, Century, Mount Isa, George Fisher, and Cannington. And it's this Isa group, Soldiers Cap group we're looking at. So Tina and HYC sit within the Batten fault zone, and we have the north-south cross-section across Tina. You can see the growth and the thickening, and there's significant variations from, I think in some areas from 1,000 meters down to, less than 100 meters on some of these packages. And likewise, the east-west section here from HYC, you can see the variation in thickness of those units. I'd mentioned there's just some of the details there on the evidence for diagenetic replacement. And I'll just highlight, so there's the EMU fault zone. It may or may not be a terrain boundary itself, but it's linked through to a major basement structure in that area. Looking at the Century deposit, it's large and fairly large and still flat lying, hosted in younger units that were deposited during inversion, and then the ore body formed slightly later during the major inversion event. The ore bodies localized, you can see the location of Century Mine here along the Termite Range fault. And I just put this one in from George Gibson to highlight the sort of features they're seeing in the seismic. If you look at his inset here in the lower right, you can see his little arrows. Those are showing on lap on that red surface. And that just means those folds are developing so that the overlying stratigraphy is on lapping to the underlying surface. So that means we have to have shortening and development of those folds happening during that deposition stage. So that's where we're getting that detailed information on extension, minor inversion, extension, more significant inversion. This one, I just want to quickly highlight. So this is the same location map, that Century here on the central gray mag image. We have a north-south seismic line shown here. And so we can see from north to south the variation in thickness of that entire package. So that's that entire Mount Isa super basin. It gets up to 8 to 10 kilometers thick. The scale there is, I think, 3.5, 4 seconds at the base of that seismic section. And you can see most of those units thin to next to nothing. So that's the Fickling group, the thinner Fickling group that is exposed on the edge of the Murphy Inlier. But we also see, so that's coming down and thickening into an east-west trending fault. And that's what this plan view map at the top shows. It's an isochore or thickness map. Now I've gone the other way. So we're going from 0 to 3,500 meters of just that river package. That's the package where we see most of the thickening, and that's the unit that hosts HYC and other deposits. It's also of interest to the petroleum industry because it's got a very high TOC. So this line, this is just another version of the line here through Century. And so that same river package we'd interpret to be the package that is thickening into this northwest trending structure. So if we have thickening into east-west trending structures and at the same time into northwest trending structures, that helps us control and understand our extension direction. And that gives us the ability to predict when we go away from the areas that we where we have this good control, we can be more predictive about what we think that stratigraphy looks like and what will be happening, a better understanding of the thickness of the river sequence. So, and again, these are structures that are related to basement. And I think I'll show you on the next line, these northeast trending structures. No, it'll come later. So Mount Isa, I wanted to show this in because I've seen a talk by Peter Ray a couple of times recently, this lower right image. So in green is the basement fault. Below that, you have the Eastern Creek volcanics, basalts that are recognized. They're altered and probably sourced a lot of the copper and or lead zinc. But the wisdom for years was that nothing went through that basal contact, and they have gone back and they've managed to find some old core, and they've shown now that there's a key structure. The key structure bringing in the fluid to the copper ore body is a steep structure that comes from below. It comes from that basement. And the highest grades are just as you go from the underlying basalts into the overlying shales of the Urquhart group, they brecciate, and that's where the highest grades are. So I think there's no doubt that the copper ore body is late and structural. I think there's further studies to be done at Mount Isa itself, but George Fisher, there's a PhD in it that's just finished that really shows there's diagenetic carbonate replacement there, similar to the other ore bodies, but it also documents several stages of mineralization and remobilization within that area that then involve the copper. Quickly on to Cannington, sitting in the east, and I'll jump out to show you the map again to show you where we've been. So it's a broken hill type. And there's a few differences with the Mount Isa type. There was a big focus by BHP in the 80s to look around Australia for other broken hill type provinces. And they focused in on the Cloncurry area east of Mount Isa. So this is one of their maps where they defined, it's shown in red, a key stratigraphic horizon based on evidence for gannite and lead isotopes. They just went back to a bunch of heavy mineral samples that they had already and reanalyzed and managed to focus in on this area. They've early on found Altea and Moronin, and then eventually found Cannington itself down here, which is the more significant deposit. So in the upper right, we have a cross-section, and then in the center, a map view of the Cannington deposit. And you can see all the various colors here, all the different ore zones. There's quite a zonation to the ore there at Cannington. It's considered to be syn-sedimentary. And as I mentioned, there are ex-halite style units in it, but the main model that you can see here at the base on the mineralizing event, we have the metal-bearing fluids coming in, and they have the juvenile lead isotopes, and they're within the sequence, so not at the seafloor, which is the key difference there. The metals are being deposited within the sequence triggered by the oxidized seawater. The alteration can be quite skarn-like and variable, but the ore body's been subsequently metamorphosed to amphibolite to granulite grade. So, and that's been a key factor in upgrading the ore body to make it more economic. So just to recap, we finished up here at Cannington, Mount Eiser, Century, and we started at HYC here. So the lead zinc deposits are dominantly considered to be diagenetic, but they have a range in age. So somebody looking at the deposit scale would say they're diagenetic, therefore they're epigenetic. I would look at the basin scale and say they're all broadly syn-sedimentary. We have quite a long period where we have this system developing, and we have ore bodies developing throughout that basin history. So a couple of quick insights. So this map really just, and all those circles just give you an overview of where I'm going to jump around and give you a bit of an overview. I'll mainly focus here on the margin of this Tain and Craton that I've mentioned a few times, and then come down and look at a reconstructed cross-section in the Cannington area. Now, this I put a cover over the top because a lot of the geophysical data sets you see in Australia are just onshore. GA just recently released a gravity map that stitches in the satellite gravity offshore. And you really, when you're working anywhere close to the margin, you really need to understand that. The two cratonic blocks I've been mentioning, Pine Creek and Arnhem itself, they lack a preferred fabric. They're of a fairly large extent. We can see all the negative circular gravity anomalies, especially in Pine Creek, which is onshore, and we have good data. So they're cratonic blocks. They haven't deformed a lot for a long period, but they're separated by linear terrains. Here, Milingimbi and Miramina, which I've just abbreviated there, along trending north-south, and at the south, the east-west trending Murphy terrains. Now, if I take that upper one off, you can see the difference. If you're just looking at that onshore area, you're going to have a very hard time interpreting those two linear terrains between Pine Creek and Arnhem. And when I first was doing this work with the NTGS, they didn't really necessarily like the idea of separate basement blocks. They could see a lot of geology that they could correlate between Pine Creek and Arnhem, and that may well be the case, but they were separated at some point, even though they may have a shared history. But when you look offshore and you see that gravity anomaly, there's no doubt that that is a separate terrain. A big positive gravity anomaly like that, and the Murphy one to the south isn't as strong, but we immediately start thinking about mafic or ultramafic composition rocks. We can start thinking there was an accreted arc, or it might be a relic suture where we had oceanic crust caught up in a collision, or a large intercratonic rock, rift that would have been filled with basalt. But the fact that on both of these, we see a paired gravity anomaly, a negative anomaly, and a positive anomaly makes me think more it's a relic suture. So that you have the lower density zone would be your passive margin, deformed passive margin. The higher density linear belt would be an accreted arc or something equivalent. There it is. So those north-south trending basement terrains localize the Walker and Batten fault zones. And we have the evidence from the gravity data, especially as we go offshore, to say that's a relict basement terrain that's been reactivated and controlled those structures, those depot centers, which in turn controlled the Tina and HYC deposits. wrong one. So to the south here at Murphy, those basement terrains were originally interpreted, and I interpreted a south-dipping suture based on what we knew about the granites in that area, but they're interpreted based on the gravity and magnetics. We now have two seismic lines going across, as well as the MT data that confirm there are crustal scale south-dipping structures in that area, and they in turn localize the other depot centers, which we'll look at next. I was changing things from the previous talk. So this image is from 2006. This was the early Oz sea base. And I threw that up there just for comparison, because even before we had all that seismic data, based on the gravity and mag, there was a really good interpretation of the extent of this depot center. So that's where we are today. I just finished a couple of months ago an update in the NT, working with the geognostics team. And so you can see I was going to go back for you. You know, that basic geometry is there. The depth scale, it probably isn't quite the same, but you can see we've got a lot more structural detail in there now. This north-south seismic line is from Chris Carson and Ladina Carr's work. But you can see these east-west trending structures I've interpreted here. So there is a bit of outcrop that we can relate to. And you can see from the seismic, we can see the southward thickening of that Eiser group and a bit of the Calvert group. And then those normal faults that were active during extension were then reactivated, and we have inversion on those structures. And this I have to show when I give a talk, because it's just such a stunning seismic line. This is the new east-west one here. And pardon me, there was a delay in release of the data last year, and we actually put the project on hold for a couple of months so that we could ensure the results of the preliminary interpretation of the seismic was included. Now, this is key for those of you who don't know the area. This seismic line shows, so here between the yellow and the blue, the orange here and the blue, we have a, say, 3 to 4, 5 kilometer thick package of Eiser superbasin rocks that sit, especially in the center here, where the basin's been inverted, they're sitting just below 400 meters of Georgina Basin. So that, you know, the moment the seismic was out, people were pegging this ground. So, you know, there's a whole exploration boom in this area based on the results of the seismic. I think Teck got some of the main area. I haven't had a detailed look yet myself. And then over here, again, glide is the NT terminology. So again, it's Eiser superbasin, which is going to be hosting those key rocks that we're interested in for lead zinc, as well as potential for petroleum. It's the Roper group equivalents here are of more interest to the petroleum industry. So when I was looking at this, there was actually a couple old drill holes here from '79 that actually intersected something they described as stromatolitic. So these are the stromatolites like in Shark Bay present day, but they interpreted the stromatolites as being MacArthur age, which confirms the age of this group. So MacArthur is the equivalent in the NT here in the up by MacArthur River and Tina. And there is a new drill hole that's just been drilled by government, MINEX CRC, and preliminary geochron supports the interpretation. So we suddenly see a new understanding and new prospectivity for these lead zinc host rocks. And this GA have put a name on this depot center, and it's what I've just highlighted there in the dashed line was the extent of the basement terrain that I've interpreted and has now been modified based on the additional data. So this is jumping a bit west to the Bonaparte Basin. If you can see the coastline there on the map, you'll see that's the border as we come down into the Gulf there. So that's the WA-NT border near Sandy Creek there. So this seismic line is just one. There's a stunning survey offshore, and it's all depth converted, just one that's been published. because it's proprietary data. But we can see the Kimberley Craton in the west, the margin of the Pine Creek Craton in the east, and you can see the thinning of the crust. Because I'm going to show you another interpreted example of this later. You can see we've had during the early Carboniferous, when we're forming the MVT deposits in this Bonaparte Basin and the Canning Basin, which just sits off this image, we've had hyperextension of the crust. So the crust has been thinned to the point the entire crust is brittle, and that means these faults can access the mantle, water can get to the mantle, and we can serpentinize and localize deformation. So that basin has been localized, and we have this extreme thinning because we had a weak zone there to start. Now, I think I might skip through this one because I realize, I know we had a delay, but time's getting on. So because I do want to show you this last example. So we've been mainly looking, there's Century, Mount Isa. We're coming over to look at Cannington. And there's these blue lines are the seismic, and I've reconstructed the M6, M5 seismic line. The other line I show will be, to show you some of the evidence, is the IG1 line here in the north. So that's what I think that basin looked like. And I did use that previous seismic image as a guide, as a model, and especially here in the west, because I'd seen Mount Isa as being one of those thick, competent blocks. But when you look at that geometry that I have there in the reconstructed cross section of the Mount Isa block, it's come directly from the present day seismic interpretation. So I've just taken that, modified it, changed the dip. I've got the Leichhardt super basin sitting over top of it. So you can see I've got the highly thin crust, a very thick basin sitting over top. And the Numel crust in the east is thinner. We've got a thinner, more tapered wedge that's dominated by low angle fault blocks. And we see that from the other IG1 seismic line that's further north. The high iron tholiites, which are the mafic magmas coming in, have a very juvenile signature, indicating they've come from the mantle, and George Gibson and colleagues have suggested that if the crust hadn't breached, it was very close to breaching. We don't know whether we had seafloor spreading. We may have. I don't know exactly how thin this crust was and whether we had exhumation of mantle or not, but we know it had to be highly thinned. Now, I've got 10 to 20 kilometers there, from 10 on the margin to 20 in the center of that depot center. That's based on the present day seismic. If you look at that seismic line at the top, we've got up to 15 kilometers of this package preserved. And in general, we don't have the entire package present. On the middle seismic line, we've got more like 9 or 10 kilometers preserved. I think there's some missing stratigraphy, the 1550 to 1520 package on top, which has largely been eroded. And around Cannington, from Cannington up to Cloncurry, with the pressure, the metamorphic conditions indicate we've had 10 to 20 kilometers of material eroded from the top. So we know we've had a lot of uplift. And the other thing I'll point out is what we see. So this Gidja structure, you can see I'm still calling it a suture up here, that was based on the original GA interpretation. I think there was an original suture there, but what we see present day is the result of the closure of this basin. So the original suture probably localized that basin, but what we're seeing present day is closure of a basin. So I'll just quickly take you one step back, because this is the timing of the Broken Hill style mineralization. So we've got significant extension in the west and placement of the Sabella batholith. This is that key middle quartz-rich unit, the Soldier's Cap group, and it's at the top of that unit that transition into some finer grained rocks as we go from extension to post-rip sag, thermal relaxation, and that's where the mineralization is localized. So as I said, we don't have constraints on how thin the crust was, but it's going to be obvious the geothermal gradient is going to be very high there and too high for our effective redox reaction. So in terms of prospectivity, we want to be thinking about these margins. But then the challenge becomes is how do we tell where those margin areas are in the present day shortened basin? Because when you look at this lower cross section, so this is at the roughly around the end of extension, although that's not well constrained, shortening, and a major shortening event followed on from this because we collided with Laurentia. So we had two major cratonic blocks colliding. We had significant shortening. And when you look at that, that inversion was controlled by what we had at the time of extension. So you start by reactivating your normal faults, but when you think about shortening that and shoving Newmal and Mount Isa close together, you very quickly see you're going to have a room problem. So you end up with larger scale translation facilitated by the carbonates in blue. And then the Newmal will be thrust beneath the Mount Isa because the Mount Isa crust is thicker and more buoyant, and its lithosphere is thicker and more buoyant. So not conclusions, a bit of a summary. Mount Isa versus Broken Hill style or Cannington. So our Mount Isa deposits, now this seismic line sits well to the south, but with the north-south grain, we can see the relative positions. So the Mount Isa style deposits are sitting over that thick component crust. We develop basins that are smaller and more isolated, and we don't see that juvenile signature. The lead isotope signature shows that we're recycling old crust. Whereas Cannington and Pegmont here in the east overlies crusts that have been highly thinned and dominated by moderate to low angle fault blocks. We see, we can interpret a vast deep basin. We have the juvenile input, we have the mafic rocks, the mafic tholiites, and the lead isotopes. And so I think there's a range of factors involved, but I think one of the underlying factors and the differences between Mount Isa and Cannington is the way the underlying crust controlled the basin evolution. I think I've got, yes. So the crust controls the basin, and the juvenile input, that extension, the high geotherm and metamorphic grade, and that in turn controls the style of the ore body. So at least part of the difference between Cannington and Mount Isa relates to the setting of hyperextension there in the east. So a very quick summary. Crustal architecture and basement structure is really important, and you need to understand that to understand the structural inheritance and reactivation. And we looked at that in the Batten and Walker fault zones that sit along the side of that large Arnhem Craton. Gidja structure is a rework structure. And for me, this is early and preliminary, and doing those reconstructions, it was partly triggered because I submitted an abstract and it was accepted, and I thought, okay, I need to think a bit harder about this and draw some images. What do I think is going on? So it's an early thought, but I think there's real value in looking harder at this and trying to unravel that present day inverted basin to understand where Cannington and Pegmont and other related deposits sit so that we can better, more effectively explore for more. I think this paper on the lab depth is very interesting and definitely worth pursuing. They've certainly highlighted there's a key spatial relationship between big deposits and that 170 contour. I don't think we really understand it, and we need to look harder at the basement and integrate the understanding of the basement, because I think the main change in thickness is probably further out. Given what I can understand in the Arnhem Craton, the main change from thick to thin is not going to come through here. There'll certainly be some thinning there because we know we've had extension, but the main change should probably be a little further over. And I think that's it. Thank you.
Well, thanks very much, Karen. That was a fantastic overview of quite a complex area, and you kind of, in some ways, simplified it, but certainly went into enough detail. And it's great to see the outcomes are leading to, new exploration, tenements being taken up and everything.
Yeah, with the wealth of data with the EFTF program, there's some really, there's been that initial move just based on that, but I think as we start to understand and integrate that data, it'll be fabulous.
That's brilliant. Do we have any questions in the room? And I might quickly jump on and look and see if there's any online questions. Paul, do you have any? I imagine somebody would.
Okay, thanks. I actually have a heap, but I'll only ask one or two. Thanks, Karen. It's fascinating to see how the understanding of Northern Australia at that scale has evolved over the last 20 years, mainly due to the extra data sets, I guess, that are coming through, and also the hard work of people like yourself in putting together the sea base, etc.
Thanks.
I guess the main questions the main question I had was, and you touched on what I think is pretty interesting, is the gradient in that change of depth to the lithosphere and the asthenosphere boundary.
Yes.
And how that's tied into these structures, for example, the Gidja suture and those other structures further west, I guess, towards Mount Eiser. What are your thoughts? You made a question on your last slide about it, but what sort of are your thoughts about how they're linked?
I think there's a link. I think we need to understand it better, and I think we need to test. Doing the calculation to create that lab depth is complex. It's not something, I'm going to approach myself. And there are different data sets and different methodologies to do it. So I think we need to review. And in the Hoggard paper, their paper is only 6 pages, but the supplementary data is 90 pages. So they do show their process in great detail through there. But I think we need to better understand that, and we need to recognise that there is a big plus minus. I just ran into Carl Zanata at GA last week or the week before and asked him about that. And he said part of the reason that they've focused on the 170 depth rather than the change, the rate of change and where are those greatest gradients, he said it's because of the resolution of that data set. He said as soon as you try and do an enhancement on it and highlight the steeper zones, you're potentially introducing more artifacts because it is not a high resolution data set. So I think I'd like to see integration with the understanding of the basement terrains, what we know from near surface, what we can now know about the crust from the seismic and the MT and the tomography, and integrate that with our lab models. And I think there's another EFT abstract by Marcus Haynes as a senior author. I just showed their difference grid. They're working on integrating more data sets into a lab depth that will hopefully give us a better understanding.
Mm. Okay. Well, thanks, Karen. I'll just ask one more question. Sorry, Nathan. And this is more showing my lack of knowledge, I guess. Particularly when you showed that boundary between the Pine Creek and the Arnhem terrains, and thinking about this lab. What is the current thinking about modern style plate tectonics and subduction? And was that occurring back, pre-1800?
But certainly by that time, and I can't remember, there has been a couple of recent papers that I sort of glanced at but didn't look in detail. So I think the transition it's in the Archean, maybe around 3 billion years, somewhere around there. So by this stage, by the time we're into the early Paleoproterozoic, then we're thinking more about active plate tectonics. So, and that's part, what I've seen when I've worked elsewhere is that somewhere around 2200, 2100, there's quite an extensional event in some of the cratons where you break up, but you essentially come together again in a very similar position. And when I look at that, it makes me think of some of the things I've seen in northern Canada where the timing's a bit better constrained. So, the blocks are similar on either side. You rift, you get some sort of ocean basin that you just close again. So, yes to plate tectonics at that time.
Karen, we've got one question online from Bradley Cave. And just wondering about the evidence for mafic magmatism at 1620. in units of the Eiser super basin or further north. Could you comment on?
The evidence for mafic magmatism at that stage, sorry, I'll look at you here, the camera, at that stage is more in the east. I don't know of mafic magmatism in the western fold belt and around Mount Isa documented at that time, but in the east there are, oh, my mind's just gone blank. Alex Brown at Glencore is doing his PhD in the Tommy Creek block, and he's done a bunch of new geochron that shows mafic and ultramafic and felsic magmatism right down to about 1620, 1618. And the Griffin paper that I highlighted, they have a bunch of mafic juvenile zircons from those from those present-day drainages at 1625 to 1630. So we can see that magmatism does go on to that period. I think the tectonic setting is less clear. It may be continued extension, or we may have some transition happening at that time.
Okay, thank you. I've got a quick question just about the scale of your observations. Obviously, we're at the Craton scale, bigger. When it comes to now some of those prospective terrains that you've highlighted and now exploring deeper and undercover, the scalability of some of the techniques that you're showing results from, they seem great for picking the kind of the terrains. Are they applicable now for exploring undercover as well and finessing some of those structures that may be controlling the actual more deposition?
Yes, I think definitely, I think so, and that's part of it. So we've got the regional seismic, and I've been working with the GSQ. We've got a product coming out soon on interpretation of the deep seismic and those main crustal blocks. So some of those deep crustal images I was showing. So we need to understand where those main boundaries are, but we can then take the seismic data sets, integrate with the gravity and mag, any drill data, anything we can pull together to get that better picture undercover. And obviously the deeper we go, the less certain we are. But for that zone where most people are going to be interested in exploring, then I think we can still use those data sets, and recognizing their resolution, we can certainly improve that undercover area.
That's great. That's very exciting things to look forward to in the future.
Yeah.
If there are no other questions from the room, I'll bring it to a close. So if you can just join me in thanking Karen one more time. Thank you. Just announced for next week's speaker, we have Nadia Kunz from UBC, who'll be presenting mitigating water risks in the mining sector and questioning really who are the water risks to, which I think will be an interesting talk. So thanks everybody, and hope to see you next week. Thanks.